Hello friends, this is Adam Cap and today we are going to discuss inflation. So this inflation is not from the economic perspective, this is more a physics perspective. So I'm assuming that you understand a little bit of inflation, what is this? Therefore, I am just giving you some scratchy thing about inflation. In this video, I'm going to discuss about the inflaton field, that the field that is responsible for the inflation, how the mathematics is giving you the idea of inflation. And let me tell you this fact that till now, we have not verified any inflaton in our universe, but the model has predicted that the universe has gone through the inflationary epoch. So, in this video, we are going to discuss that how we have arrived in this concept and what is the concept of inflaton field and so on. So, let's get started our video. Astronomers found that using the radio telescope that universe is not empty and it is filled up of some faint energy of the photons, and they came around that these photons have the energy or the temperature of the universe is around 2.7 Kelvin. So what they have expected that, okay, whatever this photon that we are capturing in the microwave region, all the distribution of the energies has to be quite same. Okay, so when we are talking about the energy, this energy is again can be thought of as a temperature. Okay, so temperature is energy and energy is temperature using the Boltzmann conversion of the energy. So they have captured using the radio telescope different photons, and these photons are not corresponding towards any galaxies or any stars and so on. These are very faint, and that's why it's corresponding to the microwave region. So what you are seeing here, that the photon have the kind of energy which is very small, like 2.7 Kelvin, and that's why it is given in the blue. So blue is the coldest photons, and here you can see the yellow region, where yellow is signifies some kind of hotness, and the red is the hottest photon. So when we are talking about the hottest photon, the photon that has the greater energy. On the other hand, bluish part, the photon does not have that much amount of energies. So it is quite natural that, okay, if we are getting the photons from the different part of the universe, or these photons are coming from the past, so it's the universe is assumed to be homogeneous at the largest scale. And here you can see that this is the map of the sky. So no matter where you go from here, the universe has to be look quite similar, and that's why we are using the theorem is called the universe is at the largest scale is homogeneous and isotropic, means that there is no any preference location, no preference angle, and so on. On the other hand, when we are seeing some patches over here, these patches, that there is a red patches or yellow patches, this signifies that if the photon is coming from the past, the early universe that we are think of, that where the photon is coming from, is not quite the homogeneous. There are some inhomogeneity, and we assume that, and these homogeneities are very important to form the structure that we are seeing, because we have the galaxies, different things in the universe. What is the origination of this matter that we are corresponding towards this galaxy and so on. So the seed of these inhomogeneities may be in the past, and this inhomogeneity is leading towards the large scale structure, and we are saying that without this inhomogeneity, the structure in this universe cannot possible. So first of all, I'm giving you the picture of the history of the universe. We are living currently over here, where the universe is accelerating. As you understand, that universe is dominated by two kind of matter or energy. One is called the dark matter, and another one is dark energy, which we are unaware of. Dark matter is about 27%, and dark energy quite 69%, and 4% of the matter that we are encounter of, or we know what we are quite of understanding of these matters and what we are made up of. So today we are here, but as we are looking back in the space, what we are seeing the past, the history of the universe. So there was a singularity there. At t is equal to 0, we don't know what had happened of the universe. We have different kind of theory that maybe the universe has no ending, maybe there were previous universe, and it has the kind of universe that we are here, then it has come into an end, and now we have the different universe, and this is kind of a uh, you know cyclic universe. Okay, so this is the singularity that we don't know anything about. So this singularity is a bit kind of vacuum energy or whatever. It says that whatever is coming out from here, the spreadness is kind of homogeneous. It means that if there is a one positive particle, it means that whatever the number of positive particle, there has to be same equal amount of negative particles. If there is one particular metric over here, then this particular metric will over here, and so on and so forth. This kind of an analogy which is I'm just giving you. This has not to be the same analogy that other people can use. So the thing is that if something is coming from the very spherical kind of thing, then everything has to be homogeneous. But as we have already stated, that the photon that we are coming, that is we are observing, is that it's not signifying that the early universe is bit homogeneous. So the thing is, the question is that what kind of thing had happened that there is an inhomogeneity in our universe. So what is the seed of this inhomogeneity? Okay, so this question has led us to think of something that after the Big Bang, what happened is that there might be some expansion of the universe, and this expansion had happened between 10 to the power minus of 43 seconds to 10 to the power minus 36 seconds. Okay, so this our model has predicted. Using the cosmological data, we have the model, we have formulated the model, and then this model is giving you that, okay, if the inflation or if the expansion has happened for this point of time, then you have the universe what you are observing today. If the inflation could have lasted many longer, then okay, this could not be possible, or it should not be lesser than this one. So these kind of bound we are getting from the cosmological data, although this is not very greater bound, but whatever it is, it's kind of thing we are explaining today. So what happened is that whatever coming out from the Big Bang, there was expansion, and from this expansion, everything, the universe has expanded, very enormously. So in this finite time, and after that, the inflation is stopped, and there is a soup of plasma, means that everything is there: the photons, the electrons, the protons, and the plasma, gluons, and everything is the proton is not there quite. Plasma of gluons, quarks, and all these different subatomic particles are there, and photons are also there, electron is also there, and here we can say that this photon and different other particles, they are basically entangled in such a way that they cannot escape one another. Here we can see that we can observe the light. Just light is kind of transparent, but during the early phase they are not very much transparent. That is the meaning. So here this region is called a very dark. We cannot know from the electromagnetic perspective, dark era. From the electromagnetic perspective, this is dark. We cannot understand. This is opaque because we cannot detect gamma. But there is another door that if the universe is quite dense, therefore there was gravitational waves, and the universe was inhomogeneous, so there was the gravitational waves, and these gravitational waves is called to be a primordial gravitational waves, and we may detect, although the magnitude of this gravitational waves is quite fainter for so you cannot in principle we can detect, but technologically we are not too much advanced to detect those kind of gravitational waves. Okay, so that is the problem, that there is some era which completely dark, we don't know about it. So this phase is called the radiation phase, where each and every subatomic particles are there. We don't know what they are doing, but it's there. Okay, the energy is very high, so there is no any atom. So as the universe becomes larger and larger, the temperature drops down, and as the temperature drops down, it means that the photon has the lesser temperature and it cannot knock off the protons and so on. So the first of all, the nucleus has bound, the atom has bound, and they have formed the light nuclei or light atoms, and hydrogen atom has formed. And once the hydrogen atom or the light nuclei, like lithium and so on, the helium has formed, then the photons has disentangled, and this is the year from t is equal to 0 to 380,000 years. Okay, This is the time where the photons has disentangled from each and every other particles of the universe. And this is the photon that we are capturing from this in the radio telescope, and this is why this photon has microwave kind of region, okay, very fainter. So that's why we can say that this photon have the source of the early universe. It cannot, and not no any galaxies can emit, because galaxy has formed after millions of years, maybe like 10 to the power you can say that 1 billion year or 2 billion years. After that the nebula has formed, and maybe after 10 billion what you can say 13 billion years, or maybe 2 or 3 billion years later, the galaxy has formed. These are called primordial galaxy, and this is called the structure formation, okay. So you understand that the beginning was very homogeneous. There was inflation, and this inflation has have the kind of potential which introduced some inhomogeneity in the universe. So we can say that inflation is required to sustain our universe, and inflation is the origination where you have inhomogeneity in our universe. That is the first requirement of the inflation, okay. Now, second thing is that when we are observing the geometry of the universe, the geometry is come out to be is equal to 0. So the curvature of the universe is around 0, and this says that the universe is perfectly spatial, okay. So you have some particular time, and this time the space is around to be flat. And because of this flattiness, you again, how you gonna defend this how you gonna explain this flat curvature of the universe? And this explanation is coming from the inflation. So there are a lot of things, like the structure of the universe is the great role the inflation is playing the part. On the other hand, there is the gravitational waves called the primordial gravitational waves, and this is again called the curvature of the universe, and so on. So this leads us to define that there has to be some kind of inflation. Okay, now who is responsible for inflation? So when we are describing dark energy or dark matter, for this kind of description, we have this lambda CDM model, where lambda stands for some kind of cosmological constant. We don't know what is this cosmological constant. And we have cold dark matter. This cold dark matter is the pressureless dark matter. And when we are modeling this dark matter, we assume that the pressure of the dark matter is 0. It has the energy density, which has to be again the positive. So we can model this thing as a perfect fluid. Okay, so we are considering that the dark matter from the early age to the later age, the equation of a state, or we can say that this pressure is always pressureless. So dark matter, the equation of the state, how the equation of the state we are defining? We're defining P is equal to omega times the energy density, and this omega is called the equation of the state. So we are assuming that from early to present age, the dark matter is assumed to be pressureless, while when universe was too young, the dark matter density was not dominant, dark energy was not dominant. But we understand that since dark energy is giving you the negative kind of acceleration, negative kind of gravitational effect, so this kind of thing has already happened in the universe during the inflationary period. So there are some components of the inflation which playing the role after it is ending, because there is some part. So suppose that inflation is coming from, let us say, some kind of field. It has the beginning, it has the ending, and after that there is some kind of residue of the inflaton that which again dominant at the present state of the universe. So on the other hand, if you try to model this inflation from the perfect fluid scenario, as you can understand that this perfect fluid scenario is not more dynamical. Okay, so here for the dark energy, we can model is using the lambda CDM. We cannot model the inflation from this perfect fluid approach. That's why we are required to introduce the inflation, and this inflation is leading by some kind of field is called the inflaton field. Let me remind you that this inflaton field, we have not directly yet observed it. It is hard to observe this directly, and the energy scale at which we are talking about inflation to be happen, it's enormous. It has already written here that it has to be 10 to the power, I think 16, or 10 to the power 16 GeV, which is impossible to create in large hadron collider, LSC. Okay, you are required to make a collider which is galaxy size of big. So in principle, you can create the inflation kind of scenario, what happens during the Big Bang. Technically, it's not quite feasible. Okay, so as I have already discussed you that in this lecture, what I am going to focus on the mathematical approach, how we can study mathematically inflation. In order to inflation, what we are, we are using there are various models of inflation. First of all, let me tell you. This first model is called maybe cold inflation. There is something called chaotic inflation, warm inflation, okay, warm inflation. There is some fuzzy inflation, and there are a lot of inflation. You can name it, and there are different models and so on. So basically, what I am now for some time being, I'm going to focus on the cold inflation. That what is this cold inflation? How we can construct mathematically and so on. So for the purpose, what I'm going to start with it, I'm going to start from the action. That first of all, we are required to write action, and the action is first of all we are required to write that okay, the universe is governed by Einstein-Hilbert action. So I can write here, first of all, the metric, the determinant of this metric, let us say g mu nu minus negative of g mu nu. Square root has to be positive in order to have the correct definition, d for x. And we have the scalar r over 2 kappa square, we can say. And then there is some action corresponding to this inflaton field. We already know that if you vary this action with respect to this delta g mu nu, then you will end up with the Einstein's field Einstein field or Einstein tensor g mu nu is equal to kappa square and then energy momentum tensor, which is coming from this matter. So this matter is basically what it is we are talking about. So first of all, let me just give you that what is kappa square. Kappa square is the inverse of Planck mass, inverse of Planck. Some people call it Planck residue, or some can prefer Planck mass, MPL. So kappa square is basically 1 over 8 pi times g Newton. I'm assuming that I'm working at c is equal to 1. So here c is equal to 1. And what else we can say, that g mu nu is equal to r mu nu minus half g mu nu times r. Okay. So this is tensor, this has to be, tensor satisfaction of the tensor, that indices in the lower indices, therefore everything has to be lower indices, and it has to be, covariant. So this is all good. And here we have kappa square T mu nu. And T mu nu can be realized for the perfect fluid is coming out to be rho u mu u nu plus, I think, rho plus P. Yeah. P for pressure and P g mu nu. So there may be maybe a plus or minus depending on it, the way you are choosing. So now in order to solve it, you have to first define what kind of metric we are using. As I have already told you that whatever happened during this phase, we are assuming that the universe is again homogeneous and isotropic. There is no need to, requirement of right now. The background we are always think of that it has to be isotropic. It has to be, direction independent, location independent. There is no any preference of any particular location. And here comes the metric for this highly structured symmetric universe is minus dt square plus a square t into dx square for the flat kind of curvature. Now people are again questioning this, that is this the metric that is actually there, or there could be some different kind of other metric, the possibility of different metrics. So people are again understanding that what could be the possible deviation from this metric and so on. Okay, and we are not introducing any kind of perturbation so far here. So this is my background metric, and let me just clarify here that this a is the scale factor, t is the time coordinate, x is the spatial coordinate. So this is the space-time geometry, and I can write over here that g mu nu in terms of metric is -1. Everything is just diagonal, a square, and a square. So this is 4 cross 4 matrix. So I hope this is the familiarity. This is this is just the very basic concept that I am introducing. So now, if you try to compute it with g mu nu or from g00, what you will get over here is that 3h square is equal to kappa square some rho from the T mu nu tensor, and 2h dot plus 3h square is equal to minus kappa square some pressure. Okay, this is after solving, after imposing this metric, after solving the Einstein's tensor, Einstein field equation, r mu nu minus half g mu nu r is equal to kappa square T mu nu, and you have rho and kappa square p. I have already written over here that what is this. Now, yet I have already told you that this T mu nu, whatever this coming from this matter, it cannot be the perfect field. And what it should be? It should be some kind of field, and the simplest field that we can assume, or maybe if people are working the dark energy, they have familiar with the quintessence kind of field, and this quintessence in the early epoch can be considered as the inflation kind of field. So this is called inflation, and what we can write over here is that people are smartly writing Lagrangian. I'm just first of all I'm writing over here this SM part. What is the Lagrangian is looking like? This Lagrangian is looking like d mu phi and phi. So this is corresponding to the field velocity and phi, and since universe is very assumed to be homogeneous and isotropic, therefore it is not depending on the space part. It is just, you can assume that this is perfectly fine if it is depending on the time. Okay, so in that sense this is velocity and this is the field, and you can compare it from the classical perspective. The Lagrangian is velocity, that x dot and the coordinate, and you can take variation of this thing, and you will get the equation of motion corresponding to it. Okay, so here you have the object delta phi. So what you can do is that delta sm over delta phi, and you will get the equation of motion over here is equal to 0. Okay, so we will get the field equation corresponding to this SM field. Okay, so the problem over here is that what is this L d mu phi comma phi? In case of quintessence, this is determined by del mu phi. I can just write, because phi is again a scalar quantity, I can write here like d mu phi minus v. And if you just contract this one by using g mu, let us say alpha, d mu phi and d alpha phi minus v, what you will end up with this g mu nu, because the spatial derivative, always mind it, spatial derivative of this phi is equal to 0. Just we are focusing on del 0 phi. Del 0 phi means that dt of phi, dt phi, which is basically d phi over dt. Okay, so here we can write here that minus z00 del 0 phi, and it will be squared, and g0 is, we have already here, that is minus 1. So that is our signature, matrix signature. I can write over here that phi dot square by 2, and here we have v phi. So again, you can by comparing with the classical mechanics, you can see that this is the kinetic energy of the field and this is the potential energy of the field, and Lagrangian to be defined in such a way that kinetic energy minus potential energy. So what could be the SM I can write over here that integral d4x square root of negative of g, and this L of d mu phi comma phi. Okay, so here I am introducing square root of minus g. Okay, so this square root of, when people are when you have taken this delta g mu nu, then you are ending up with t mu nu. Okay, so this is the energy moment tensor coming from over here. So this square root of minus g is ensuring that this field is coupling with the gravity, and this coupling is called the minimal coupling. Okay, here I am not introducing anything, just it is coupled like that. There is a fiber, as we are used to think like the curvature of the geometry, and onto which there is some kind of field is propagating and so on. So basically the interaction is kind of minimally, there is nothing like no component is multiplying just like r, or maybe r mu nu and so on. So if you have certain kind of curvature explicitly, then it will become a non-minimal kind of interaction. So I hope so far it is clear. Okay, so here the Lagrangian over here, everything is written, and let me just give you for the brief thing, so somebody who is not properly understand this kind of things, I can write r over 2 kappa squared plus square root of again minus g let us say I am writing over here, and delta mu phi, and this is phi. Now you take a variation of this action with respect to delta g mu nu, you will end up with Einstein field equation. Delta s over delta phi, you will end up with the field equation. And this field equation has no dependency over here, just only over here. And the metric component will arise, or if you take this one is equal to the 0, then what you will end up with that phi double dot plus 3h phi dot plus dv over d phi is equal to 0. Okay, so here what I have shown you that Lagrangian is equal to phi dot square over 2 minus b phi, and when you take a variation, there is a lot of indices, and when you're contracting the indices, you will arrive, there is some kind of Christopher symbol arising, and because of the Christopher symbol there is 3h phi dot. Now what you can see over here is that we have to first try to understand what is the meaning of this equation. This is also called as the Klein-Gordon equation. Okay, so you can also see in some textbook or some paper, you can realize this equation like this: delta phi plus dv over d phi is equal to 0. Okay, this is also written. So this delta is given as that phi double dot plus 3h phi dot. So that's why it is again called as the Klein-Gordon equation. And when you have the universe of particular kind of metric, then this kind of equation of motion you are getting. Now what is the meaning of these particular quantities? Now this is the acceleration, because field is phi dot is the velocity, and phi double dot is the acceleration of the field. dv, v is the potential of the field. So let us say the potential could be anything from here to here to here, and on which field is, let us say the field is some kind of rolling ball, and the field is rolling on its particular potential. So the potential is going to play a very major role in this kind of particular field. Okay, now what is the meaning of 3h phi dot? We have from the Newton's perspective, if you have the spring and you attach with the mass m, there is a k. So if you displace by some particular distance, then you can say that F is equal to minus of kx, and I can simplify, I can simply write here over here that it will experience some kind of acceleration which is minus of kx. So this thing is basically the same thing like minus of kx, and you may think of it like what do you say, x double dot is equal to minus k by m into x double dot is equal to minus of omega square into x. Omega is particular frequency, so here x double dot plus omega square x is equal to 0. So again, this has some particular thing that, okay, this is the acceleration and this is something, okay, and this is coming from the potential energy or whatever you can say that. Okay, so suppose you have the potential, and you can easily find out that what is the potential is half maybe kx square or m square omega square x square. So du by dx would be m omega square, not m square, m omega square, and you will have dx. So this is like x double dot plus du over dx is equal to 0. So this is again the similar thing as we have already written in terms of field, but the problem is that there is an additional thing, 3h phi dot. Now this is the velocity, and we have already seen that suppose there is some kind of viscous medium. Okay, so what I can introduce that F is equal to minus kx and maybe some kind of constant b, and there is some velocity vv. So this is coming from the viscosity term. So there is a velocity if you are adding in this equation, it is a viscosity, and similarly what we can say that here is again a viscous term of this force, that when it is rolling, it is not kind of very free fall. There is some kind of medium which is coming from its geometry or maybe some kind of interaction, and from which it will particularly losing its motion and so on. So this is the viscosity through which it has to be rolled. So that is the particular meaning of the inflaton field, and this phi is not quintessence field. Now it has the meaning of inflaton field. So I hope up to here everything makes sense. Okay, now you may realize over here that, okay, so this is the field equation, but I have already written over here there are two different Friedmann equations. These are Friedmann equation. Okay, after solving the Einstein's field equation, this is called the first Friedmann equation. This is again labeled as the second Friedmann equation. Okay, So this is the Hubble velocity, Hubble parameter, and this is the Hubble acceleration term. And h is defined as a dot over a. A is a scale factor, and a dot is basically giving you of a dA over dt is written as a dot. So whenever I am giving you any kind of particular dot, its just meaning is d by dt of that particular quantity. Okay. So yeah. So with this, now I have to determine that what could be the energy momentum tensor of this field. So I'm not going to again compute this because it's going to take this lecture to be enormously big. So I'm just giving you that the energy density of this field would be of phi dot square plus v of phi, and the pressure of this field is half phi dot square minus of v phi. Now you may have realized that if you have the perfect fluid, we have P is equal to omega times rho. On the other hand, if you have this field kind of structure, you cannot simply define omega. Or you can easily define here that omega is not just written over that omega into times rho. Here omega is also phi dependence, and that's why I can define here that half phi dot square minus of v phi is equal to half phi dot square plus of v phi. So this is again time dependent. On the other hand, it was not the more time dependent if you are assuming that field if you're assuming rather than some perfect fluid. So that's how the dynamics is playing out, that you are again still comparing with everything with a perfect fluid, or that is your standard technique, but here the things are really complicated and really more dynamic, so therefore it can give you more tools to dig deeper on what could have happened if the inflaton is driven by this particular type of field. Okay, so now over here phi double dot plus 3h phi dot plus v dv over d phi, and what I'm gonna instead of writing v comma phi, okay, after here. So now in order to understand that what could be the phi, you have to first define what is the v, and then you can know that okay, what this is the particular field. Till now we don't know what could be the field. So first of all, you have to assume that this is your answer about potential. The potential could be exponential kind of potential, maybe it's half phi square kind of thing, like parabolic kind of potential. So there are different kind of aspect, and the potential could be maybe different, maybe anything. Okay, so the problem is that what could be the condition? I've already told you that inflation has begun, and then it has lasted for a few minutes, and then it has ended. So now we need to establish a mechanism through which we can say that this is the particular time period for which inflation had happened, and after that it has ended. So how are we going to impose those things into it? That is a very important thing. But before going to that, what is the meaning of expansion of the universe? So first of all, we have to clear that how we can find or define the expansion from the general relativity aspect. I have here 3h square is equal to, let's say, kappa square rho, and 2s dot plus 3h square is equal to minus kappa square p. Okay. So what I'm going to write here, that if I'm writing here 2s dot is equal to kappa square p is equal to minus kappa square p over here. So 2s dot is equal to kappa square with negative over here at p plus rho, isn't it? So here has dot is again the Hubble acceleration minus kappa square by 2, if I am everything is correct. Yeah, p plus rho. Okay. Now you may realize over here that this p plus rho, s dot, h is always a positive quantity, means that Hubble, in order to have the accelerating kind of expansion, Hubble has to be positive. Now this Hubble acceleration, we have already done it, that if acceleration is coming out to be positive, it means that something is accelerating. If it is negative, then it is deaccelerating. It means that s dot has to be greater than 0. So kappa is positive, p is again what you can say, it is not so p plus rho has to be in such a way that it has to counter this negative, isn't it? So how we can counter this negativity from over here? Well, what we can do is that it is possible, because rho of any particular field or anything cannot be, energy density of anything cannot be negative. So what we can realize is that it has to be, greater than 0, but P can be negative. And how is this possible? If it is possible when your omega is negative. If omega is coming out to be negative, then it's possible that this negative is gone and then you have the Hubble acceleration. Otherwise, it's not possible. Okay, now once it is done, now how we can, represent this in terms of, field? I can simply plug it over here, that kappa square by 2, P is half phi dot square minus V, and rho is half phi dot square plus V. And now you may realize over here is that VV is cancelled out, and this phi dot square, therefore kappa square by 2, and here you have phi dot square. So now the problem over here is that, so what we are saying that phi dot square is again a positive quantity, but what we can expect from here is that, let's say that S dot H is equal to A dot over A. So S dot would be A double dot over A minus A dot square over A square, and this A dot or A double dot over A would be A dot square is equal to H square. So I can just write here A double dot over A minus H square is equal to kappa square by 2 phi dot square. Why I'm doing it? That is importance. A double dot over A minus H square is equal to kappa square rho over 3 minus kappa square by 2 phi dot square. So here everything is, very transparent, because A double dot, A is the scale factor, like the distance. A dot is again showing you the how the A is changing. A double dot is the acceleration. It means that how the space is, how the universe is basically changing. So A double dot over A has to be, greater than 0. It cannot be 0. A double dot by A is equal to minus kappa square. I can say over here that this is half phi dot square, and there is a negative sign, because if I'm taking this negative over here, then I will get the 1 by 3 rho. Okay, so over here what I can realize that half phi dot square minus 1 by 6 phi dot square, and this is again V with 1 over 3, if I am doing everything correctly. So minus kappa square, what I am doing over here is a 3 over 3, 3 minus 2, 6, 2 over 6, 1 by 3 phi dot square, and over here I have V over 3 and minus kappa square over 3, I got phi dot square minus V, A double dot over A. Now it is more transparent. Now how we can have the acceleration is greater than 0, you may realize over here is that this negative has to be gone. And how it is gone? When the V is very greater than V dot squared. So the potential of the inflaton field has to be greater in order to have the accelerating kind of scenario. If it is not the case, then acceleration cannot happen. So how the acceleration can begin? The first criteria of the inflation is that the potential of the inflaton field all the time has to be greater than the kinetic energy of the field. So that's why I told you that in the inflaton, in the cold inflation, gone inflation, the potential is playing an enormous role in order to produce the inflation as well as the end the inflation. It means that whenever you have the potential is greater than the kinetic energy of the field, you have the inflation, and in order to end the inflation, we have to tweak the potential in such a way that V has to be lesser than phi dot square by 2. So I am not saying that this is the condition, but here is the kind of condition that okay, if the kinetic energy is greater of the inflaton field and greater than its potential, then we can have non-accelerating kind of scenario, and how the inflation has ended up. So this is the very crucial point, that potential of the inflation field has to be greater. You have already maybe you have already used this term, and this is how we have arrived over here, that how this is established. Now one more important thing is that in order to study the inflation, what people used to do, do is that one required to introduce some slow roll kind of parameter. There is one slow roll, first slow roll parameter, second slow roll parameter, and so on. And in the core inflation, the most important parameter is that is E1, and E1 is defined as minus h dot over h square. So how you can derive it? You can just derive by following. So first of all, you define a parameter epsilon 0, and which is kind of like some Hubble inflation, means that during the inflation, Hubble is kind of in a very constant, and the Hubble width is time dependent. So this Hubble parameter like n plus 1 can be derived by following log of epsilon 0 over dn. Okay, and what is this dn? This is dn is defined as dn is equal to h times dt, the Hubble parameter and this one. So now if you just integrate over here, is that like if you can write over here like d of log h in over h, which is time dependent, and h into dt, and if you will just do everything, you will realize that this is h dot over h square. I am not doing anything, and this is e1, so e0, d of e0 and something. So let me just again rewrite here, sorry, e1, so epsilon of n plus 1 is equal to d of log of epsilon n over d of n. So this is the thing you can define, and n is called the number of e folds, and this is the e folds that is determine that how long the inflation is there, that it is the from this perspective, from this n, one decide that what is the interval of the inflationary epoch. Okay, so now this is a very interesting quantity. Now if you just plug it over here, that epsilon, what is this epsilon? H dot over h square. So what is what we have done over here, that s dot is kappa square by 2 phi dot square. So this is kappa square by 2 phi dot square, and h square is equal to kappa square over 3 and rho phi. Kappa kappa will be cancelled out, therefore I am just giving you phi dot square by 2, and here the rho phi would be half phi dot square plus v. This is the energy density of corresponding to this one. This is epsilon 1. Now for the inflation to be happen, v has to be far greater than phi dot square. So one, you can easily realize that this I can write over here 3 phi square phi dot square over 2, and this is just only a v. Now here we are assuming that since the potential is very enormous and the field is rolling over this potential, so this is slowly rolling. In order to last the inflation, the field has to roll slowly. The rolling of slowly in such a way that the acceleration of the field is nearly equal to 0, and that is the meaning of the slow roll parameter. Because if the field is highly fast, we say it is not rolling slowly, it means that the inflation is never going to happen, isn't it? In order to have the inflation to begin and to last for some time, the field has to roll over the inflation for quite time. Therefore the acceleration of the field is enormously lesser than this velocity. So the field equation, you have this 3h phi dot plus dv over d phi can be equal to 0. Now I can express this everything in terms of potential. Here I can just write here that v dot is equal to v comma phi over 3h. So epsilon 1 can be written over here is that phi dot square would be, and here is negative sign, I can write here 3 by 2, phi dot square would be v comma phi whole squared over 9 h square times v. And 3 cancel, I got 1 by 6 v comma phi square, and h square is, again I can write over here 2 times 3 and 3h square times v, and again I can just plug in the Friedman equation, v comma phi whole square over 2 v, 3h square is equal to kappa square and half phi dot square plus v. So now this is a very amazing thing. Like what we can do, again we can apply that v is very greater than, so I can just write over here v phi square 2 kappa square, and this v into v will be v squared. So you see I have translated my epsilon 1 into completely the potential, and you have already seen this in the standard textbook. that first people have defined it from the Hubble perspective. You have field velocity as well as the potential, and now I am determining everything in terms of potential. Okay, so this is the epsilon 1 from which you can realize v dot square over 2 kappa square v square, and it has to be lesser than, very much lesser than 1 in order to have the slow roll approximation. So this is called the slow roll parameter. And similarly, by differentiating this d of log epsilon 1 over dn, you will get epsilon 2. So this you can do it, and you can check that how this is thing. Mind you that in order to have the cold inflation, we have just only one requirement, that epsilon has to be lesser than 1. We are not very much required that what should be the epsilon 2. One more thing, that log of epsilon 1, this has to be positive. Otherwise it cannot be log of negative thing cannot be, log cannot take a negative argument. Similarly, here you can see that v phi square, again it ensures that positive, v square positive, kappa square is again some positive number, therefore epsilon 1 is again a positive thing. So here we can say that everything is defined over here, and I can also consistently get epsilon 2. I can consistently construct epsilon 2. Okay, so we can also easily calculate over here that 3h phi dot over dv over d phi. You can dv over d phi is equal to 0. But the problem over here is that without knowing the potential, the problem is that you cannot determine your phi dot. This is one of the major tasks. Now if you just ignore dv over d phi, and you may say that again I'm going to go for trine Gordon, and somehow your dv over d phi is approximately 0, and with this term is very very close to 0, and in such a way that this is compatible with this phi double dot 3h phi dot. If this happens, then we are going in ultra slow roll kind of inflation, which people are too much interested in these days. And by using nothing, just you can say that phi dot is your particular some object. I can just write here d phi dot over phi t is equal to minus 3. H I can write over here is this is phi dot, so I can just write your phi dot, and I can take h right here, d phi over h dt is equal to minus 3 phi dot, is again a very simple thing. D phi dot over phi dot is equal to minus 3 has dt. I have already told you this is dn. I'm going to integrate it, and this will give you log of phi dot is equal to minus of 3n, and phi dot is minus 3n. So this is proportional to, I'm not writing any particular constant, so you can easily set constant, maybe with some n star, there is a phi dot star and so on. So this is the particular kind of slow roll. What will happen if the universe, if the kind of potential where the potential is extremely flat in such a way that the slope, this v phi is called the slope of the potential. The slope of the potential is nearly zero. It means that there was some kind of in the slow roll kind of parameter where there is a finite amount of v comma phi. V is still there, V is not going anywhere, but in the potential there is a regime where the potential can be nearly too flat, isn't it? And the field is rolling over here, and in such a way that the field velocity is again decreasing and decreasing and decreasing. So it reduces in such a way that it is nearly comparable with this phi dot. We have to compare with anything, because otherwise what will happen that 3h phi dot is equal to 0, which cannot be balanced. So we cannot write it. So in order to have ultra slow inflation, we can say that the v comma phi is approximately 0, and phi double dot plus phi dot is compatible. Therefore the equation of motion is now here, and here we can see that phi dot is approximately e to minus 3n. So for an example, if you take any kind of let us say suppose you have the inflationary field, and inflationary field you have some background and plus some kind of, let us say, fluctuation, or maybe some kind of scaling. You are saying that maybe I can scale up or scale down, so it is some kind of constant. So you may realize that phi dot can make this thing scale independent. So it means that whatever is going to happen with the slow roll, it is scale independent. Similarly, the same thing you will realize in the ultra slow roll, that it has to be also scale independent, which is we are going to discuss more thing, that we are going to compare what is happening in slow roll, what is going to happen in ultra slow roll. So but this is the complete framework to understand, to realize the slow roll parameter, what is the meaning of inflation, how the inflation have started, how we can end up the inflation, and how the radiation epoch has started, and what is the why we are thinking field as a dark energy, and so on, how we are establishing the fact that potential has to be greater in order to produce the inflation, and so on, and why it should be normal. So there are a lot of things, and in this series I'm going to cover everything: cold inflation, as well as I'm going to cover this warm inflation, fuzzy inflation, chaotic inflation, as well as I'm going to talk about the stochastic inflation, which is more on the statistical approach. I will try to upload more videos on dark matter and dark energy by analyzing some different research papers, so you can understand better from the research perspective. So this is Saddam Leonardo Cap signing out, and please don't forget to subscribe my channel and share it to your friends. Bye bye.